So welcome back. This will be the last session of FDF for this year. I'm Eva Goussiou, electronics engineer from the BIMS department here at CERN, and we continue this session with solutions to everyday digital problems. The first speaker is Valerio Nappi. He's a colleague here from CERN. So Valerio is an engineer for the accelerator sector at CERN. He's working on FPGA and SoC real-time control systems for power converters. His work includes FPGA development, embedded systems integration, and software gateway co-design. Today he will present his work on the Zynq UltraScale Plus for real-time control. Thank you, Valerio.
Thank you for the introduction. Hi, everyone. Good morning. I'm Valerio, and as I was saying, I work in the power converters group at CERN. So what we do is we are responsible for operating about 6,000, developing and operating about 6,000 power converters. So for this purpose, we developed one platform that we can adapt to all the power converters we have, from few watts to some megawatts, so from really a shoebox size to a building size. And right now we operate two platforms that are called FGC2, FGC3, where FGC is the function generator controller. And we are in the process of developing the FGC4, which is the latest generation of our converter controller. This converter controller is tasked with regulating power to the ppm level. And this is really important because these power converters here at CERN, for example, control the magnets in which the beam travels. And to achieve accurate control, we need very accurate currents. So where are we now? We have our latest system, which was designed 15 years ago, which is FGC3. It's a very modular system. It comes as a portfolio of some tens of cards. And each of these cards have FPGAs, have CPLDs. You see, we're talking about really old parts right now. Most of those are discontinued, not all. And all these components are interconnected with buses that run through the backplane, that run between cards. So overall, this platform was very successful. It allowed us to control really thousands of power converters, but it's now in need of a successor. And for this reason, we are developing the latest FGC4. So our task for that is to be able to control a power converter and to control a converter that can go as fast as 100 kilohertz regulation range. That means that we repeat our control every 10 microseconds, which is tight time budget. So what did we think for this? Well, the spoiler is in the title of the talk. We had a look at Zynq UltraScale, especially because it combines fast processors. So it combines fast CPUs inside this APU. So we have 4 cores that can run up to 1.5 gigahertz, and then an FPGA fabric. So typically, when you control a power converter, you will read some ADCs, you will read some digital IOs, you will run your regulation, and then write some output. This output is most likely a PWM that is then controlling power devices, but it can be DACs, it can be digital IOs. This SoC would look like the ideal candidate because it provides very tight coupling between the CPUs and the FPGA, where we could instantiate all our control modules, ADC readout, filters, except the standard CPU FPGA path, so the standard communication path, turns out takes about 10% of our time budget. That is in our tightest constrained case. This is actually quite simple to measure. You instantiate a timer counter in your FPGA, and you sample it repeatedly. And you see that between your samples, with no stop, the code is written in assembly here, you get to the timer most of the time in 590 nanoseconds. But this is 93% of the cases, which is not good for our power converter, especially considering that it can last up to 1 microsecond. Again, we have 10 microsecond regulation budget to do all our math. If accessing a register takes us 1 microsecond, that's clearly not good enough. We cannot afford that. So we had to find a solution. Well, the obvious solution is, can we use the DMA? Of course, if we have not the processor transferring the data, well, that's really convenient. You'll just find the data there. So there's a few ways, a few ports that are controlled by the PL, by the FPGA, in which you can push data. And there is one that is notably very interesting because it's stated in the documentation as low latency path between the PS and the accelerators provided in the PL. So this port is mastered by the PL. So of course you can use it read and write, but the transactions are initiated by the FPGA. And it provides a very, very short path. You see all the other ports go through an incredible amount of interconnects, while this taps straight into the cache controller. With its own limitations. So this is AXI port, but can only support 16-byte and 64-byte transaction. They need to be aligned. And of course, can get cache miss if you're writing to a location that is not written in the cache. So then my task was, well, let's characterize this port, because of course there's nothing in the documentation. They say it's low latency. What does low latency mean? We're going to find out. So first of all, what even is this level 2 cache? So we said this ACP port targets this level 2 cache of the CPU. Well, what is a level 2 cache? If you look in the Cortex A53 core that Zynq UltraScale has, you have 4 cores in our case, and each owns level 1 cache. It's very local. It's 32 kilobytes of data. Then there's 32 more for instructions, but for what we carry is 32 kilobytes. And then there's another cache, which is the level 2, which is what the ACP port writes to and reads from, that is shared between all the cores. Well, how much time does it take for our CPU to access this cache? Luckily, it's quite easy to do this test. And there was someone that came before us, the blog Chip and Cheese, that wrote a super good article about this. And we replicated this test. And you can really see as your packet size grows in the x-axis, your latency time increases. And it increases exactly with the size of the cache, as one expects. So you see on the leftmost side of the graph, you have the level 1 cache, 32 kilobytes. And as long as you're reading and writing within this 32 kilobytes, you get 4 or 5 nanoseconds time to read, which is very good. Unfortunately, we cannot target this cache. So our next best option is the level 2 cache, which you can see can be read and written in about 17 nanoseconds. Well, that starts to look much better than the 600 we saw before. But of course, the data needs to get there. And then you see, of course, focus on the blue line for now. You see, once you go out of the domain of the cache, then your time explodes because you have to fetch this from the DDR. And what you see in the orange instead is, what if you, instead of random access, you access in order? Well, then the prefetcher will do its job and speed you up a bit. So that's also very interesting to see, well, prefetcher actually works. OK, well, then how fast can we put the data there? So there's 2 modes, as I said. One is 16 bytes, which means 128 bits in one transaction in AXI. And the other one is 64 bytes. You see both in the graphs, in most of my graphs. FYI. So you see on the top graph, this is what happens when you randomly access some data through ACP. Most of your reads fall within 100 nanoseconds, and then some take a bit longer. But then this is not realistic for a power converter because we're not going to be accessing gigabytes, megabytes of data. What we really care is a very localized amount of data. And this is very interesting for a cache because it means it will be already in the cache. So you'll get a cache hit very often. So what happens is if you instead point to the same address, you get the result that is showed in the second graph. Now 99.99, etc. % of your writes fall within these 100 nanoseconds, which is very good because it means that we can put the data there most of the time in 100 nanoseconds with very, very few exceptions. You see these graphs are all in log scale. So the counts you see at the bottom, these are ppms, parts per million. Really, most of the data gets transferred within 100 nanoseconds. And if you consider then you have about 17 nanoseconds to access it, well, we already cut our time in a quarter of the time. Of course, you cannot fit anything that the power converter needs in 64 bytes. So how far can we stretch this? Well, what if we, instead of hitting one cache line repeatedly, we hit 2, and they are next to each other? Well, it turns out you can extend it quite a lot. actually the results don't change even if you hit 64 cache lines. So turns out once you extrapolate, as long as you fit more or less in the level 2 cache, which is again 1 megabyte, you can still achieve this performance. So you see up to 64 cache lines, it is this test that I did. You can still do it within 100 nanoseconds. Now then you consider that, yes, okay, this is true, but this is per 64-byte write, so you have to repeat it every cache line you want to hit. Fine. But then very fast converters, in our case, will not need to access a lot of data, so a couple of cache lines are really enough. So this is suitable for us. And then, yeah, okay, you're going to put your data there. How are you going to notify your CPU that the data is there and is ready to be read? Well, we need a way to synchronize it. How do you synchronize two systems when one is a CPU? Of course, you use interrupts. Yes. Well, how do they perform? And this is particularly tricky to measure, especially when you consider that you want to measure an event that exists across two domains. One is your FPGA, and one is your CPU, and they don't share a common knowledge of time. So how are you going to time that? I came up with two ways to measure it. They are very similar. In one case, case A, the PL, the FPGA holds the time. In this case, you start a timer in the FPGA, and at the same time, you also start an interrupt. Then from the interrupt routine, you read the FPGA timer, you sample it, and that is going to tell you how much time it took for the interrupt to be executed. The problem is you're adding a delay, because as we saw in the first slide, you need some time to access the PL. The other side is case B. You can hold the timer in the CPU. So in this case, we use the performance clock that is shipped with this A53 ARM core. You start a timer, you go to the PL, you trigger a GPIO line. This line gives you an interrupt, and then in the ISR, you sample again the timer that you started in the PL. Again, you add a delay when you go and trigger the timer. Is there no way out? This is the best I could do. And in fact, when you think about it, the two cases are not mutually exclusive. You can run the two tests in a single run. So you start a timer, go and trigger the interrupt. The interrupt also releases a timer in the PL. And then once you sample it, you sample both the timer in the PS and in the PL. And the results are surprisingly similar. So if you look at the top slide, you see that the two approaches, the PS and the orange and the blue, the PS and the PL timer are very, very, very compatible. But they are going to be, of course, affected by the exact same systematic error, because in both cases, you're going to have to access the PL, and that's going to come with a delay. I could not find a better way to measure this. So I had to stop here, basically. And I just found that most of the time, the highest bound is about 800 nanoseconds. This is not too bad, because as long as the jitter is not enormous, you can compensate for this. You can just send your interrupt request 800 nanoseconds before. Fine. Well, then, how much jitter do we have? This is a bit easier to measure, because if you programmatically send an interrupt every this much time, in my case, 10 microseconds, which is the realistic case, then you're going to be able to sample the same timer without accessing the PL in the PS. And this is going to give you the idea of the jitter. And you see, most of the cases happen every 10 microseconds plus minus, well, within a 75 nanoseconds window of this 10 microseconds, which gives us reasonable jitter if we are aware of that. And then the last question I try to answer is, well, what happens when other things are happening in the system on chip? What happens when the interrupt controller is being spawned by something else? The easiest way I found is I take one core and I have it run ePerf Ethernet test, and this is going to spam it with traffic. Oh, now we're going to have a problem. So you see in the top graph, this is the first graph we saw, the time that it takes the CPU to access the FPGA. And you see the blue one is the base case. Once you start having Ethernet traffic, the tail becomes longer. It's not too dramatic. In the accessing the PL time can go up to 1.5 microseconds, but if you're not relying on that, all fine. What was more dramatic is the effect that you have on the interrupts. So you see on the plot, the yellow tails are cases where Ethernet traffic is active, and there is a certain pause between each test I do. I found that if I do my test continuously, even with Ethernet traffic, I don't see much of an effect. But instead, if I pause my test for a bit, that is 10, 100 microsecond, or 1 millisecond, the results change. And in this case, the change is dramatic, and it gets much, much, much worse. In the worst case, by pausing 1 millisecond per between each test, the time can stretch up to 3 microseconds. I cannot explain this. If you can come and talk to me, send me an email, I have no idea why I see this effect. But it's there. I measured it, and I measured it reliably. No idea. So to wrap it up, accessing the FPGA through the standard HPM FPD ports will take too long for us. What we can do instead is we can DMA the data. And DMAing the data into the level 2 cache will take about 100 nanoseconds per 64-byte transaction. And then the CPU will take about 17 nanoseconds per word. So this is per 32-bit word to access the level 2. Other takeaway is interrupt latency is surprisingly hard to measure. I'm able to say highest bound must be around 800 nanoseconds. But of course, there is an effect that I cannot get rid of in my measurements. And in any case, latency doesn't matter too much once it's constant, because you can compensate. Of course, you cannot do the same for ADC data because it's going to be new every time, but interrupt you know in advance. You just send the interrupt pulse a bit before. What matters is the jitter, and I measured this to be about 75 nanoseconds. So the conclusion of my work is we can go ahead with the UltraScale Plus system on chip and do our controller on that chip. That concludes my talk.
Thank you very much, Valerio, for a thorough benchmarking. Your answers or questions?
Very nice talk, thank you. If it's so difficult to tackle the transfers between PL and PS, have you considered running the timing critical things completely in PL?
We have, and we can see this will become a thing at some point. Right now, though, the control is written by our power converter experts that are experts in the domain of power electronics, and they are not experts in FPGAs. So what we do is we write with them, most of the time they write C code that runs the control, because historically they've been used to do that. We can see that for very fast converters, at some point, we can push this to the FPGA, and perhaps exploiting some partial reconfiguration to be able to have one master PL design and then put converter-specific control. Again, important point here is this family of devices control about 6,000 units scattered at CERN, operating 24/7. So it has a big impact every choice we make. So, and most of this is specific per converter, so it should become a lot of FPGA designs. But yes, I think it's a good approach.
Yes.
Did you have a look at how access activity on the other core affected the access into the L2 cache?
Yeah, so this is actually, I did measure it. I can share the data. I don't have it in this presentation. It does affect it a bit, but this is stated in the documentation. The documentation makes it very clear that any access is competing between the ACP ports and the other cores. So any access to memory is competing there. So of course, you're going to get worse results.
Thank you for the nice presentation. I think a lot of people can benefit from knowing this information that we got. I have just a couple of questions. First of all, are you using the Zynq CPUs in bare metal, or you are using it on top of Linux? You're using bare metal.
So we actually have a mixed approach. We use multiprocessing, and we have 2 cores that run Linux, and in this course we run our front end, and then we have 2 regulation cores that run bare metal.
So you're also using the R5
we are not using the R5
okay.
simply because it is too slow. So it's limited to less than half the clock frequency, and to get the throughput we need to go for the faster APU, for the faster A53 cores. So we are targeting 2 cores in the same CPU.
Okay, understood. Thank you.
Which is also nice because it gives you access to the shared memory between the cores in the cache. So you can communicate between the cores, between Linux and bare metal faster.
I thought that the R5 would have been a little bit more predictable, and that's...
I thought the same as well. I did the same tests. The latency is much bigger. Because from the FPGA to access the RPU is placed in the low power domain, which means you have to cross a lot of interconnects to get there. And the result is the latency is huge, it's massive.
Okay. Thank you so much for the findings.
Hi, this is Daniel from Estron in the Netherlands. I was wondering, have you considered doing a simulation in an HCL simulator in order to witness the transactions in a wave window and possibly time them using the simulator's timescale?
No, I have not. It's perhaps interesting if the models are good, but I have not run them. It could be an interesting development indeed. Thanks for the suggestion.
And Valerio, your work seems of general interest. I was wondering, you mentioned some benchmarking from somebody else regarding the cache latencies.
Yes.
But what about the interrupts? Are you the only one?
So there are some papers. There's one that came out recently about interrupts, and they have more or less the same results as me. So we kind of agree on that. They published it before, but I have a bit of a different approach.
Good. I don't see more questions, so let's thank Valerio once more.